Okay, welcome back, everybody. Before I continue with our chapter, we'll be done with chapter 7 today. I promise. It seems like we've been on it for a long time, but it is one of the longest chapters, and a lot of important information that you really need to progress to the other chapters. So anyway, any questions? Now, here, let me let in a couple of people here. All right. Okay, well, let me share with you where we left off. Okay, we start here, but I'm going to back it up for a second, kind of rehash a little bit. At this point, what we've been talking about is Lewis dot structures. We started off with the atoms, and that was very straightforward, specifically only for the elements in the A elements from group Roman numeral 1 to 8. Okay. Knowing how many valence electrons they have, it was a matter of a function of just adding dots around the symbol of the element. Okay, so that's pretty straightforward. Then we moved into actually making Lewis dot structures from actual compounds. Okay, and it's very straightforward here also. In that one, we add up all of the valence electrons that every atom brings to the structure. So we have 1 hydrogen, 2 hydrogen, whatever it takes. We add them all up, okay? We end up with a number which is always divisible by 2. Why? Because what I do is I divide that by 2, the sum of the valence electrons to give me the number of pair, only because I like to work with the pairs rather than deal with the individual valence electrons. When you have like 8 or 10 of them, not a problem, but when you start getting into 32, that's a lot of dots to take care of. So using the line to represent 2 electrons is a pair, is the manner that I go. So we add them up. We had this example, HCN. So hydrogen brought 1, carbon brought 4, nitrogen brought 5, the total of 10 valence electrons. And the important part about this valence electron math here is that is what you got to work with. You cannot add or subtract those valence electrons. Those are the atoms that brought the valence electrons to the structure, okay? So we're going to keep track of the number as we progress. So we end up with 5 pair in this particular structure of HCN. All right, so we'll always be given who is the central atom. Remember this, we have a central atom. That is when we have two or more atoms bonded to a central atom. When you only got 2 atoms in the structure, there's no central atom, obviously, right? They're just sitting there, okay? Either one could be the central atom. So here we have carbon listed as a central atom. That is denoted by it being in bold color or bold print, or it's underscored, okay? Or you'll be told in writing, okay, carbon's a central atom. That means that everything else is bonded to the central atom. We have 5 pair, we can very quickly bond all the other elements to the central atom. And in this case, we can quickly bond the nitrogen and the hydrogen each and draw a line between them to designate a pair. That meant that left 2 pair from the original 3 pair. And so now with those 3 pair, you put them on any of the atoms that you want to, other than hydrogen, because remember, hydrogen will only have 1 bond, okay? It's duet. It doesn't have an octet rule, it has a duet. So once you place all the pairs of electrons that you calculated, do a count. Make sure you're still doing inventory, making sure you still got 5 pairs. And sure enough, if you look at that structure there are 5 pair of electrons, so you're good to go. Now at this time, you check the octet for all the atoms except hydrogen, which is a duet. Hydrogen's happy as the way it stands. You don't have to do anything else with it. Carbon only has 2 lines attached to it. That means there's 4 electrons. It needs 2 electrons. Excuse me, 4 more. I meant to say 2 pair. 4 more electrons fulfill the octet. Nitrogen, as written in the first structure, is happy with 8, but carbon is not. So at this point, you start creating either double or triple bonds. That's that's the limit, either a single, a double, or a triple bond. There's no such animal as a quadruple bond, only single, double, or triple. With the pair that you initially calculated. Okay, so now we end up with the final structure here highlighted in white, where you have on nitrogen 3 bonds, which is a triple bond, and 1 pair that is a lone pair. It's not bonded to anything. And so if we count all those electrons are on nitrogen, you have 8. So nitrogen is happy. Carbon is sharing those 6 electrons on the right-hand side with nitrogen. So you can also count them toward carbon. And then on the left side, it's sharing 2 electrons with the hydrogen. So carbon now is stable with 8 electrons around it. Now, so we know about hydrogen. So that is the structure that we come up with. Then following that, once you come with that structure, you then generate general structure. And we need the general structure, the ABX, remember that? A, B, X, and EY, okay? That's our general formula for our general structure that we're going to create. A represents the central atom. There's only one A, always will be. B represents whatever is bonded to the central atom. So here we have both a nitrogen and a hydrogen bonded to it. And so we put a subscript 2 to designate the 2 atoms bonded to the central atom. And E represents any lone pair on the central atom. Note that there are no lone pairs on the central atom. So in this case, we don't have an E, so our general formula is AB2. That general formula, then you take to the shapes table, and that's why you need the shapes table. And you refer and you look for AB2, which is the first entry under the general formula, and then that tells you the molecular geometry. There's a picture of it right there. You can see how HCN is bonded, where you got carbon here in the middle. Maybe this is the nitrogen, and maybe that's the hydrogen. Okay, its name is linear, and the bond angle between the 2 species that are bonded to the central atom is 180 degrees. Okay, so that's how we get that information. Now let's go back to that. What we're going to do now is apply the same process to a different type of compounds that we call polyatomic ions. Okay. Now these, for the most part, are covalent compounds, but they are put together in such a manner that they form ions. And they're either going to have a positive or negative charge on them. Some examples of that are in the periodic table. Pull it back up. And if you look at the periodic table down here in the bottom left corner, you see some common polyatomic ions. These polyatomic ions come as a unit. We don't separate them, don't do it. They come together as a unit. If we ever need more than one of these units, we put a parenthesis around it with a subscript to designate more than one, okay? Now you can see that majority of them are negative charge. So most of them are anions. See all of them with a negative charge. We got NO3 with a negative charge. The one that has a positive charge, probably the only one we're gonna work with, is that NH4+, which is called the ammonium. Note that each one has their own unique name. Okay, so that OH is called the hydroxy ion. It wouldn't be called a oxygen hydride, anything of that sort. It's called hydroxide. Same is true with this one here, nitrate. That's the name for this one. Again, wouldn't be called nitrogen trioxides, any combination name of that sort. Okay, has its own specific name. Most of them are negative. Only a few are positive. And that's important to know because we're going to learn how to do the Lewis dot structures for these types of polyatomic ions. And the one thing we need to know is what kind of charge they have. okay? Because that is going to tell us what we need to do with the sum of the valence electrons that we calculate, which we calculate in the same manner, okay? We add up all the atoms and the number of valence electrons each one brings, and then we're either going to subtract or we're going to add a value depending on the charge of that polyatomic ion. For example, if it has a negative charge, like the sulfate, the nitrate that as you saw earlier in the table, we're going to add a number to it, okay? And that number depends on the charge of the polyatomic ion. A lot of them are -1, some are -2, some are -3. So we add whatever that charge is to the sum of the valence electrons that we calculate. If it's a positive cation, then we subtract a number from the number of valence electrons that we calculated, okay? Then at the end, because it is a polyatomic ion, we put a bracket, not a parenthesis, but a bracket around the whole molecule, and then on the upper right, we place the charge, okay? So let's try this one here, the ammonium ion, which is really the only one listed in the polyatomic ion table. So we do the same steps as before. We add up all of the elements, all the valence electrons from every element. So we got 1 nitrogen, okay? And nitrogen is in group 5, so we got 5 electrons for nitrogen. All right, there are 4 hydrogens, and each one brings 1, so we have a total of 4 valence electrons for the hydrogens, okay? And it is a positive ion, and so we're going to subtract from the sum. And so we subtract 1 because it's a positive 1, and so we have 8, okay? As valence electrons to work with, or otherwise we have 4 pair. All right, now nitrogen is the central atom, so we very quickly can write nitrogen, and those 4 hydrogens are bonded to the central atom, so we can quickly make 4 lines to represent the bonds of the hydrogens to the nitrogen. So that took care of 4 pair. All right, so we have 0 pair left to have to work with, so we're done. We go back and check the octet. Nitrogen has 8 electrons around it, 4 bonds, and the hydrogens are happy with their 2. So everybody's happy, and now we can write a bracket and then put the charge in the upper right corner. I just tend to circle it to tell me it's a charge, put a circle on the charge. So that is the structure for the polyatomic ion, given the formula that we have. Now, we can continue with the shape. We continue in that we generate the general formula like we normally would. So we have A and then B4. We got A, which is nitrogen, and we got 4 hydrogens around it. There are no lone pair of nitrogen. So that is our general formula for the ammonium polyatomic ion, which means that going back to the shapes table, okay, we look for AB4, which is right there. And it has that general structure, as you can see there. And, you know, this easily could be nitrogen in the center, and then the hydrogens all bonded around it, okay? And it has a general shape. Name of the shape is tetrahedral, which is the most common type of shape that molecules have. And that bond angle between them is 109.5 between what is bonded to the central atom, between the hydrogens in this case. All right. And that's in essence what I just explained right here, okay? And that is for polyatomic ions, and then we rewrite the formula with the bracket around it to designate it as an ion. Note that for the neutral species, the non-ions, we didn't have a bracket around it, right? This is only for the ions. All right, well, let's try a couple more. Most of these are definitely, they're negative polyatomic ions. Again, we don't know the name of them, but I'll tell you anyway. It's called bromine in the upper left-hand corner, but we don't have to know what they are. But we do know that Br is underlined and it's a central atom. We know that oxygen, there's 3 of them. And we also know that what we're given, that this whole species has a -1 charge. So it's a polyatomic ion, okay? So we do what we've been doing. Bromine brings 7 valence electrons, okay? Oxygen, there's 3 of them. Each one brings in 6 because it's in group 6A. So there's 18 valence electrons. It has a negative charge, so we need to add a 1. So that means that we have 26 total valence electrons to work with, and or 13 pair, okay? And now we got how many pair to work with? We do what we've been doing, nothing different. Just because it's an ion doesn't mean we change what we've been doing. All we've done is we were going to either add or subtract a number depending on the charge. And so bromine is the central atom, and there's 3 oxygens bonded around it, so we can very quickly just bond 3 oxygens, okay? And so that takes care of 3 bonds. So we got 10 pair to work with. So now you can, as I said before, what I just prefer to, if I can, put them on the outside elements and work my way in. So I'm just going to put them on all the oxygens with the 10. Keep it in mind, I can only put 8 around each atom. So I can put 3 around 1 oxygen, right? Because it's got 4 bonds around it now, 4 pair around it. So that's happy. So I move on to the next one. So that's 3, and that's 4, 5, and 6, 7, 8, and 9, okay? And so now I have 1 pair left over. I cannot put any more on the oxygen. So the only logical place this thing can go is on the central atom, which is the bromine, okay? And so now I'm done with the structure. I put the bracket, okay? And it has a -1 charge. I put a -1 charge on the upper right bracket, okay? And that is the Lewis dot structure for this particular polyatomic ion. I can also generate a general formula, no different than before. So I got A, B, 3, because there's 3 oxygens around it. And there is an electron pair in the central atom. So my general formula is AB3E. Okay, AB3E. I can go on and look and determine its structure, and sure enough, just like ammonia, here it is. It's AB3E. This is the particular shape. Notice that these 2 dots with that kind of elliptical shape, it just represents an orbital that contains those two electrons. And this shape is trigonopyramidal, okay? And the bond angle is less than 109.5. And again, the reason we know it's less than 109.5 is because those lone pair of electrons, they take up a lot more space because there's 2 electrons. They're not bonded to anything. They're sitting there on the central atom, and they repel each other, okay? And that causes that bond between the other bonded elements to shrink and to be decreased, because those lone pair take up a lot of more space than a pair that has been bonded. All right, so that is the structure right there. All right, now let's try the next one. This was SO4 -2. This is the one called the sulfate polyatomic ion. Sulfate. We'll be dealing this quite a bit with this one a number of times, a number of places. down the road here. All right, continue the process. We got one sulfur bringing in 6 valence electrons. We have 4 oxygens, each one bringing in 6. So we got a total of 24 valence electrons coming from the oxygens. And then we add 2 more because the charge of the sulfate ion, okay, which gives us a total of 32 valence electrons or 16 pair, okay. And so, as before, sulfur has been marked there. You can see that sulfur is underlined. So sulfur is the central atom. There are 4 oxygens bonded to the central atom, so I very quickly bond 4 oxygens to the central sulfur. Notice that sulfur now is done as far as electrons. It's got 8 electrons around it. So whatever is left, I definitely cannot put them on the sulfur because I got 8 around already. And so I got 12 to work with, 12 pairs. So the only place they can go, obviously, would be around the oxygen. So that's 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. 13, 14, 15, 16. We still have 16 pair. Okay. We put the bracket up. Excuse me, it's -2. Okay. And that is the structure for the sulfate ion. General formula, AB4. You can look that up, and that's called tetrahedral. So it's a tetrahedral structure with 109.5 bond angle between the oxygens. Okay. All right. So here we go, right there. Now, CN negative, that's called the cyanide. If you look at the polyatomic ion, it's similar to the HCl we did earlier, except the hydrogen's missing. Okay. And we have what's called the cyanide ion. So same thing, carbon brings in 4, hydrogen brings in 5. We're gonna need to add 1 more. Notice if you forget to add the 1, you end up with a 9, and 9 is not divisible by 2. So that would tell you, hey, I gotta go check, make sure I've added or subtracted. Okay. All right, so that gives you add 1. And you end up with a total of 10 electrons, okay? And you end up with 5 pair. And so we end up with that structure. Notice that in there, you got 5 pair. But let's say, for example, instead of adding 1 like you did right here, let's say you subtracted 1. And so you got 8. Right? And you end up with 4 pairs, what you calculate, right? Well, if you got 4 pair, that means that one of these, I'm going to highlight with yellow, is not there. And so no matter what you do, you know, you got 1, 2, 3, 4 pair, there's no way that I can make an octet. And so if that occurs to you, that happens, then go back and check your math. Make sure that you, for a negative, you added and did not make the mistake of subtracting instead of adding. You know, that's an honest mistake. It does happen. Okay. But when you get down to actually making the structure, no matter what I do to adjust the 4 pair that I supposedly calculated incorrectly, I can't make it work. I can't make the octet work. So that's a flag to tell you, go back and check the math. The same is true if you do the opposite. You add more, you calculate 1 pair more. Well, you end up in a position that I cannot put that lone pair anyplace because everybody has the octet fulfilled. So that again is a flag. I got to go back and check my math. Okay. Okay. All right, so so much for Lewis dot structures. This is basic. This part of the talk is labeled VSEPR or VSEPR, valence shell electron pair repulsion. This is no more than what I've told you about how the electron pair have to, because they're negative charge, okay, are going to repel another bond, another electron pair, such that they maximize their distance from them. And that defines how the structure comes out, depending on where these electrons are, okay? So we're gonna go through all the different shapes that we discuss, okay? And I've already introduced to you the general formula makeup of ABE. A is the central atom, B is all of the atoms bonded to the central atom, and E is the lone pair, any lone pair on the central atom, okay? And so the most common, the simplest structure is a linear species. When you have two atoms just bonded, the only structure they have is simply a linear, just by default, okay? And that space field model is shown here on the far right. Also note something here, we got two chlorides together. There's something that we talked about before called the electronegativity, which you can be coming up here in a little bit. Notice that these two chlorides are bonded to each other. They both have the same electronegativity. So that bond that they share, that tug of war with that electron, that's a shared tug of war, if you were. There's an equal sharing of those electrons in the center between the two, okay? Simply because the electronegativity of those two atoms are the same because they're the same atom, right? Another one shape is called the AB2, which is linear. We talked about carbon dioxide and came up with this particular structure here, okay? Again, linear simply because all the atoms in the final makeup of the structure are all in the same line. It's linear, just like that one there, okay? We do have one called trigonoplanar, in which the bond angle all the way around, you can see, is 120 degrees. So it's kind of a flat species, and the bond angle is 120 degrees. We call that linear, trigonoplanar. Its general formula is an AB3. An example of that is down on the left side, that is formaldehyde. You may be familiar with that. Maybe back in the high school days when you were cutting up a pig or something that was stored with formaldehyde, which they find later on this stuff causes cancer, so stay away from it. Here on the right side is what we call the space field model to give you a kind of a space three-dimensional perspective of that particular shape, okay? The most common configuration is the tetrahedral. That is a central atom with four atoms bonded in the four directions. Now, the optimum configuration is as follows, because remember that bond right there, we got electrons there, we got electrons there, electrons in that bond, and so forth, okay? And so when you have these electrons all around, they are going to position themselves so they have the maximum distance away from each other because of the repulsion, and they end up with this general tetrahedral configuration, which is pretty common for a lot of chemical compounds out there. Tetrahedral, 109.5 degree angle between the atoms that are bonded to the central atom. Now we have the AB2E, where here E is telling us we have a central lone pair of electrons on the central atom. And in this case, sulfur dioxide, because the nature of the beast, we got one sulfur, two oxygens, there's another extra pair of electrons being brought into the table, and the only place they can go to is on the central atom, okay? Now, that lone pair, again, you will want to think, well, you know, it's almost like a trigonoplanar. If this was something bonded here, we will have this AB3 kind of structure. And the thing is that we got a lone pair here, and they occupy a lot of more space than a bonded pair. And so the result is this bond angle gets kind of broken down in less than 100, the anticipated 120 degrees. You know something interesting, SO2 has this particular structure. Carbon dioxide, on the other hand, we just did that earlier, showed you that earlier, we end up with this structure, which is linear. And we would think on first observation, CO2 versus SO2, maybe very similar, but you got to remember that sulfur is not in the same group as carbon and therefore brings more electrons to the table, valence electrons. And we end up with a lone pair on the central atom, squishing that angle in a little bit tighter. Okay, let's see. We went through ammonia, NH3, and that has the structure of trigonal pyramid, and that is given there. The three-dimensional model, normally they should have maybe shown a lone pair. This is where the lone pair of electrons would be on the central atom, and the result, they occupy a lot of space, causing this bond angle to be much less than the 109.5. So these will be less than 109.5 degrees. Now, those lone pairs in the central atom, just the fact that they have lone pairs in the central atom makes this molecule a polar molecule. We're going to be talking about this, okay? With covalent compounds, we're going to talk about polar bonds and nonpolar bonds. And from that, we're going to talk about polar molecules versus nonpolar molecules. And the best analogy I can think of is the difference between water and oil. We know those two don't mix. We know also that water is classified as a very polar solvent, and oil is classified as a very nonpolar solvent. And by learning the polarity of the molecule, it would tell us a lot of information with respect to physical properties and things like whether it would be more soluble in water or it would be more soluble in oil. So a lot of other things we're going to learn. But before we can get into that, we're going to learn about polarity, and we're going to get into that here in a bit. Okay. And then we have a good example here would be water for the AB2E2. Water has two lone pairs in the central atom. And you can see here that this would be two lone pairs. Not giving it justice, but those lone pairs are in the central atom there, really bending this angle here. In fact, water is it is, to my knowledge, the most polar solvent that we have. Water, and it solvates a multiple things. All right, so that's AB2E2. And so summarize all this. Hopefully what you should need to be able to do is, one, draw the electron dot structure of both a compound or a element, okay? If you make a compound from that information, determine the shape and the bond angles. And so recall how you do that, add up the valence electrons, put it all together, determine the general formula, use the shapes table and to determine what the geometry is and what the shape is and what the bond angles are, okay? So practice on these two right here, pH3 and ozone. That is the formula for ozone. There's 3 oxygens involved there. So, so one of these oxygens, consider it as a central atom, and those 2 other oxygens are bonded to it. See what you come up with respect to a electronic dot structure, and maybe determine the shape and the bond angles, okay? If you look at pH3 and think about it, it's in the same group as nitrogen, NH3. So these very similar. All right, so what we got to do for a second is talk about bond polarity. And what do we mean by pole? Well, you're all familiar with a pole. I don't mean a pole where you're, something's hanging from a pole. We're talking about a plus or a minus. The Earth is a pole. We got a north and a south pole, okay? So that is classified as a pole. A magnet has a pole, the north and the south, right? Another thing, your electronic device, if you're running off a battery, that battery has a pole and has a positive and a negative side, okay? So we had talked about two types of bonds. Write this down. We had the first type, which dealt with ionic bonds. We call that ionic bonds, and that was a combination of a metal and a non-metal. Okay. Now, in these type of bonds, there are or ionic bonds slash compound. Okay. We have a full positive charge and a full negative charge. They come together like magnets, if you will. It's electrostatic charge. Then we talked about covalent bonds. Now, with respect to covalent bonds, these are a combination of two nonmetals. Now, there are equal sharing and unequal sharing. A covalent bond is a sharing of a bond, a sharing of electrons in a bond. But it's not that simple. We have some bonds where there are equal shared. In other words, those electrons are being distributed amongst the two atoms that are bonded together equally. And we have that bonds that are shared unequally because one atom tends to want to hold on to electrons or pull the electrons closer to it due to electronegativity. Okay. And so you might go back and refresh your memory of electronegativity, and that is a measure of an atom's affinity for electrons and pulling the electrons onto itself. Fluorine was the most electronegative element, and all the trend was from left to right, bottom up. The electronegativity increased. We use fluorine as our benchmark. Anything closer to, if we compare two atoms, we determine who's more electronegative based on how close they were to fluorine. Yes, every element up there has their own electronegative value, and it's not necessary to memorize all 118 values of electronegativity. Okay, all you got to remember is fluorine is the most electronegative. And if I'm comparing a bond between a carbon and a nitrogen, I need to know who's closer to fluorine. Then that tells me who is more electronegative, which tells me who's pulling the electrons onto themselves. Now, when the electrons are equal and shared, okay, then we have what's called a non-polar bond. There's no pole, so we no non-polar. It's equal sharing, tug of war going on, equal sharing. When one of them, the atoms are bonded and they have more electronegativity than the other one, then we call that a polar bond. Okay, so in general ways to say this is this. If I have an A bonded to an A, I have a non-polar bond. Why? Because A's, they're equal. There's an equal sharing of that electron in there. If I have A bonded to, let's just say, generically B, then I have an unequal sharing. So I can, just by looking at the structure, right away determine whether I got a polar or a non-polar bond, okay? Just by knowing that they're unequal. The only exception is a carbon-hydrogen bond. A carbon-hydrogen bond is a non-polar bond, and the reason is because the carbon electronegativity and the hydrogen electronegativity by all means is simply the same. And so they don't have, even though they're different, their electronegativity is essentially the same. It's a non-polar bond, okay? Now, what does this mean? Well, let me direct you to the course website. Yeah, on the course website, under the modules, there is additional resource module. If you click on that, I showed you this before, there's a variety of simulations in there that will help you visualize a lot of the concepts that we dealt with, okay? And so let me click on this shapes one first, for example. You pull that up, you got a simulation, just select a model here. And what this does, you can grab this model and move it around, and I can add things. So for example, I want to add four single bonds. Notice they're movable, but when I let them go, they fix themselves in such a position that they are spread out as far apart as possible. I can remove one and add a lobe. See what happened to it when I did that? When I took a bond and got the trigonal, the geometry, how it changed, and I put a lone pair. See how that geometry changes. So anyway, you can go in there and play with the different structures and make your own, so you get a good idea of how the electron, using that, how the electrons affect the general shape of molecules. Okay, let's go back to it. Now select molecule polarity. Another simulation occurs. Go ahead and select the two atoms. Okay, now I have two atoms here. Let me click it, partial. Okay, now down at the bottom here in the scale, I have a sliding bar that I can adjust the electronegativity. Right now, the electronegativity is essentially the same, okay? I got them set the same. There is an equal sharing of that bond. That gray line there in the center represents a pair of electrons that are being shared. Now, if you look at the scale on the top, you go on the far left, which says positive, and the far right, which says negative. That is the character of what happens to an atom when I change the electronegativity. I'm going to take the atom B, and I'm going to change it with some other atom that has a different electronegativity. So I'm going to increase the electronegativity. Notice a couple of things happening here. Okay, one, the redness in B, the color increases. That indicates that that area has become more negative. Again, think about it. The electronegativity increases. I'm pulling electrons more onto B, resulting in a more electron character around B. Well, the result is this, that A now is kind of, its electron density has decreased. So now it has more of a positive character to it. And we have created what we call a dipole, two poles, a negative side and a positive side. Also, you can see this arrow is starting to be created. That arrow, the point points toward the negative side, and then the tail end of the arrow points to the positive side of this bond. Okay. Another thing that occurs that hopefully you can see, this symbol looks like this. Let me try a different color here. Symbol kind of looks like this, and you get a plus sign, or it's just, okay. That's a lowercase delta, okay. And that plus tells you that that has a partial positive charge or a partial negative charge. Notice that it's right here and right here. You have generated a dipole. A dipole is there, and it's a function of the electronegativity of the two atoms together. Now, what effect does it have? Well, I can do this. I can increase it, and now you can see how dark red has become and how dark blue is happening. Also, this thing is movable here. If I put this, let me clear the plate a little, my clearing. If I put an electrical field there, wow, the partial negative side of that bond gets attracted to the positive plate and the negative gets attracted to the negative, okay? As those crazy electrons have an effect on the molecule. All right, so this is what we're talking about, creating a polar bond. Now, many molecules, just by the nature of the beast, because there's two different elements, automatically have a dipole. They automatically generate a dipole, okay? Which means that this is a polar bond, which then affects the total properties of the molecule, depending on multiple things of which we're going to talk about. So take a look at that simulation, play with it so you can become more, because this polarity thing comes back over and over and over again. It's very important factor with respect to how molecules react, why certain things boil at a certain temperature. We can do some compare and contrast between molecules and say that this one's going to boil at a higher temperature, this one's going to have a higher viscosity, many other physical properties that we're going to learn about later down the road here. But it's all related to the polarity of the bond, which is related to the polarity of the whole molecule, okay? All right, so when a covalent bond has equal sharing, as I stated, we have a nonpolar bond. And add something else to this. When your molecule has all nonpolar bonds, guess what? The compound, the molecule itself is nonpolar. With respect to solubility, that would expect it to be more soluble in oil than it would in water, okay? Because of the polarity. A covalent bond where those electrons are shared unequally, well, that is a polar bond. And there's a positive side and a partial positive and a partial negative. We say partial because unlike ionic bonds where you got a full charge, positive and negative, covalent bonds that are polar have a partial, just a little bit of negative character and a little bit of a positive character, not a full-fledged charge. And it's all related toward the electronegativity, which we use fluorine as our reference point, because fluorine is the most electronegative element that we have, okay? And we use it as far as telling us its position relative to fluorine. So if we are comparing two different elements and that fluorine's not involved, okay? We know noble gases don't have electronegativity because, again, their octet is full. And the trend, as we can see, we got fluorine, let's say fluorine sitting right here. So that's a trend. So if we're going to want to compare, let's say, a bond between, say, we got a bond between carbon and nitrogen, we want to figure out, okay, which direction does that pole go to? Well, carbon is somewhere about right here. Nitrogen is about right here in the periodic table. Nitrogen is much closer to fluorine, which tells you that nitrogen will be the most polar element in this particular bond, which tells you that there's going to be an arrow going from the carbon to the nitrogen, which tells you that there's going to be a partial negative on the nitrogen and a partial positive on the carbon, okay? And let's say we wanted to compare between, let's say, a bond between oxygen and fluoride. Well, there's a no-brainer here. Why? Because we know that fluoride is the most electronegative element. So automatically, that dipole arrow is going to the fluoride. We got a big partial negative on the fluoride, partial positive on the oxygen, okay? That is a driving force for, as an organic chemist, when we're making new compounds and create new compounds, we look for sites on the molecule that have a dipole. that allows us to do reactions on the sites, because we know that areas that don't have a dipole are difficult to get to react. We really have to do some tough things to get it to react. But those areas that have a dipole area, we can react and do reactions and make new compounds. And like a lot of antibiotics, you know, they're all basically the base unit, the same, but all the different derivatives, they're possible because these compounds had a dipole someplace, somewhere, that we can change things a little bit. And maybe that little change makes the antibiotic a little bit stronger. Sometimes it makes it a little weaker, less effective. Yeah, depends. All right, so nonpolar covalent compounds. All the diatomic elements are nonpolar. So I have no fear of ice cold beverage, right? All of them are nonpolar. Also, any carbon-hydrogen bond is a nonpolar bond. Again, simply because the electronegativity of carbon and hydrogen is essentially the same, okay? So it's a nonpolar bond. All right, let me hurry up a little bit here. All right, so this is the rehash of what I just talked about, being that two different nonmetals, we're going to have a polar covalent bond, okay? And so things like carbon, hydrogen, hydrogen chloride, sulfur fluoride, silicon nitrogen, all of them are polar covalent bonds simply because they are different elements bonded together, you see? You don't have to look up anything. You just know they're different. The only exception is carbon hydrogen. Carbon hydrogen always will be a nonpolar bond, even though they're both different elements, okay? And so we use the symbols to designate which direction the polarity is going in the bond. I introduced the arrow. We have the arrow, the polar arrow, polarity arrow, and the partial negative and the partial positive. Okay, so if we have a bond between carbon and fluoride, then the arrow goes from left to right. Okay, designating the fluoride has the partial negative sign because it has the strongest electronegativity, is the strongest electronegative element. So it pulls those electrons tightly. And that tends to make some very strong bonds with fluoride. That's why fluoride supposedly is a very good species to put in your tea, because you know it makes good structures, strong structures. All right, oxygen, hydrogen, obviously two different elements. Boom, we got a polar bond. The direction goes from right to left because oxygen is a lot more polar than hydrogen. So we get a partial negative on the oxygen, partial positive on the hydrogen. And then the bond between phosphorus and chloride, okay? We find the chloride to be much closer to fluorine, therefore the chloride is a lot more electronegative. Again, we didn't have to memorize anything as far as absolute values for electronegativity. We just find the relative position on the periodic table relative to fluoride. And so the polar bond goes from left to right here with the partial negative on the chloride. Okay. Obviously, the noble gases, they're happy. They got the octet. There's nothing's gonna happen there. They have no electronegativity. Okay, they're stable. There's no want for electrons. Okay, so here we're gonna ask to add the delta notation. That's the partial negative and the partial positive, and ask to add the polarity arrow. Okay, so remember the arrow points to the most electronegative element. Here we got carbon and oxygen bond. Find their position relative to nitrogen. We find out that oxygen is a lot more electronegative than carbon. Therefore, the arrow goes from left to right with the partial negative on the oxygen. Nitrogen and fluoride, no, don't need to go any further because fluoride is the most electronegative. That's it. And so automatically it goes from left to right here, partial negative on the fluoride. We did oxygen and hydrogen, but in this case, it's written from right to left. Okay, it could be written the other direction. All right, let me see, let me shut something down. I just got notification, my internet's a little. Okay, maybe that help out a little bit. We got chlorine and carbon. Again, the chloride is a lot more electronegative. I meant to say chloride, not chlorine. It's a lot more electronegative based on its position relative to fluoride. So the arrow here goes from right to left. And then hydrogen and carbon. No delta notations, no polarity arrow, simply because the electronegativity of both of these is fairly the same. Therefore, we have a non-polar species. The previous four examples are polar bonds. Carbon hydrogen has a non-polar bond. Okay. Here you ask, okay, what are these bonds ionic? And if not, are they polar covalent or non-polar covalent? Well, obviously, again, if it's ionic, that means it's a combination of a metal and a non-metal. And the only one there that I see that has a metal is sodium chloride. Okay, so that's the only one that has an ionic bond. And then the arrows and everything, the delta don't apply to it. Okay. But BR, bromine is nonpolar. Again, electronegativity, each one has an Ian value, but they're both the same, equal polarness, equal sharing. So bromine is nonpolar. PF is polar, different atoms. Okay. Ionic sodium chloride is an ionic bond. And FBr, again, is a polar covalent bond. And so the first one, bromine, is a polar, non-polar covalent bond. Then the next one is a polar covalent bond, ionic bond for sodium chloride, polar covalent bond for the last entry. Okay, so polarity is very crucial. Okay? It's going to be coming up again and again and again. And so, you know, but just think of it as a tug of war between the electrons. And when the two species doing the tug of war are the same, then we got equal sharing, we got a non-polar species. If they're not the same, then we got a polar bond. Okay. All right. So here, simply they're asking, is it ionic, polar, non-polar? First one, sodium chloride. You got sodium right out the bat, you know that's ionic. Okay. HCl, non-polar. Polar or ionic? What do you guys think? HCl. Anybody want to take a shot at that? HCl, aka hydrochloric acid. Is it ionic, polar, or a non-polar bond there? Is it an ionic bond, polar bond, or non-polar bond? What do you guys think? Okay, break it down. Could it even be ionic? Is hydrogen a metal or a non-metal? What about chloride? Metal, non-metal? Okay. Well, both of them are non-metals. So it's a covalent bond. Okay. And they're different. You got hydrogen and chloride. Therefore, you have a polar bond. Okay. HH, hydrogen. They're both the same atoms. Automatically, don't have to go any further. It's a non-polar covalent bond. Then we got chloride and carbon. Obviously, it's covalent. They're two different elements. Okay. So it is a polar covalent bond. Carbon and hydrogen. One of the exceptions of two different elements that are a non-polar covalent bond, because the electronegativity of each one is essentially the same. We got oxygen, okay, two different elements, or two the same elements, it's obviously nonpolar covalent, okay? One of the diatomics. Then we've got potassium and oxygen. Well, that's an ionic compound, simply because we got oxygen, and we've got oxygen bonded to a metal, potassium. So it's an ionic compound, a bond. And then the last one, we got phosphorus and fluoride, obviously covalent, and we got fluoride, two different elements involved there. So we got polar covalent, okay? Polar covalent. So if we needed to take it this one step further and draw the arrows, then we would then draw the arrows for hydrochloric acid in that direction. Maybe I can draw them better with it here. Draw them in that direction, okay, for that bond. From carbon to chloride in that direction. And from phosphorus to fluoride in that direction, okay? All right. Yeah, bear with me a few more pages and we're done with this chapter here. All right, so this brings us to this part, which is very important. All right, we just talked about the bonds. Now we're talking about specifically the covalent bonds, okay? Now, the type of covalent bonds a molecule has will define what is the overall polarity of a molecule. Now, all ionic compounds, they're polar because they dissolve in water, either 100% or much less percent, but they still they are soluble in water in variety of amounts. Okay, covalent bonds a little bit different here. Covalent bonds, they're either going to be polar or nonpolar. And the ones that are polar tend to be a lot more soluble in water than the ones that are nonpolar. That helps us out when we looking and doing a compare and contrast down the road in the other chapters. As a general guideline, all nonpolar bonds in a molecule result in a nonpolar molecule, okay? An example of that would be something like methane, got carbon and 4 hydrogens. All right, all nonpolar bonds, you got 4 of them, all of them. All of them are, it's a nonpolar molecule. Okay. When polar bonds do not cancel out, we have a polar molecule. Now, what does that mean? What I'm trying to say? Okay, let me back up and regroup a little bit there to help you understand this part of it. The arrows that we've been drawing, okay, represent what we call a vector. Now, this part is not important right now, but I'm trying to demonstrate what's going on here. Vectors in mathematics are moieties that have direction and magnitude. So they have to give you direction. So if I tell you go north, that doesn't mean anything. That's not a vector. But if I say go north 10 miles, that's a vector because you got direction, magnitude, and magnitude 10 miles and direction go north. Okay. These arrows have a magnitude involved with them. And we're going to just arbitrarily just say, let's say this has 5 units in the right direction, in the positive direction here. This is the negative direction, and that is the positive direction, just like a scale. Now, if I have an arrow going in the opposite direction with the same magnitude of 5 units, we're not too worried too much about what the units are right now, but they're 5 units, guess what happens? This arrow on the left is going in the negative direction. So I'm going negative 5 miles to the left, and I'm going positive 5 miles to the right. And guess what? They cancel each other out. Okay. So if I have a polar bond going one direction, and I have another polar bond going in the opposite direction within the molecule, the polar bonds cancel out, and overall, we have a nonpolar species. Do we have an example of that? Yes, we do. Look at carbon dioxide. Remember, we came up with this structure here, okay? Now, carbon and oxygen is a polar bond. And therefore, its arrow goes from carbon toward oxygen, because oxygen is a lot more electronegative than carbon is. And that's on the right side. So there's a partial negative on the oxygen and a partial positive on the carbon. Now, on the other side, guess what? We have another polar bond going to the left side. So we end up with a partial positive going in the negative direction and a dipole going in the negative direction of carbon dioxide and one going in the positive direction. And so we got net equals 0 equals non-polar molecule. Okay. If we look at sulfur dioxide, we got one polar bond going to the right and down. And then we got another polar bond going left and down. Then they do not go in opposite direction. I mean, they're going in opposite direction, but not exactly in opposite direction like the carbon dioxide. So they don't cancel each other out. So this guy, sulfur dioxide, again, because of the lone pair of electrons in the central atom crushing this angle, bond angle, making it smaller, results in the polar bonds not canceling out, and we end up with a polar molecule for sulfur dioxide and a non-polar molecule because the polar bonds of carbon dioxide cancel down. Okay, they're also additive. If I were to put these two units down here in the same direction, in other words, I got one going that way for 5 units, one going that way for 5 units. Guess what? I got 10 units going together in the right direction. So these are vectors, these arrows. And so any place, anywhere that that bond cancels out, we end up with a non-polar species. If they don't cancel out, then we end up with a, let me restate that. If they cancel out, it's non-polar. If they don't cancel out, it's polar. If we look at, say, carbon, again, the carbon tetrahedral, we had 4 hydrogens, 3-dimensionally. I'm trying to write those. Well, we know that the carbon-hydrogen bond is non-polar anyway. So this has 4 non-polars. But if I take one of the hydrogens and I replace it with, let's say, a chloride, I now made a polar bond. So I got 3 non-polar bonds and 1 polar bond. Overall, I got a polar molecule. Okay. And if I replace it again with place another hydrogen with another chloride, I still have a polar molecule because those 2 non-polar bonds do not cancel out the polar bonds. And the 3rd bond, I still have a polar molecule. It is not until the 4th one is replaced with the chloride. Here I got 4 polar bonds, but because of the geometry, the tetrahedral geometry of these 4 polar bonds, is such that they all cancel out. So when I replace all 4 hydrogens with chlorides, and now I'm back to a non-polar molecule. Okay. And so this part of polarity is very, very important. We need to make sure we grab a hold of this concept. Okay, there's carbon dioxide, you're canceling out. Okay, and therefore we end up with a non-polar molecule. All right, we talked about methane. Methane is all non-polar bonds, so it's going to be non-polar molecule. Okay. Now, how are we going to know it's polar out? Well, here's where the Lewis-Dow structures comes into play. We have to, and you may I'm going to have you go through it. I need to write the Lewis dot structure for PCl3. And when you do that, you should come up with something like this. Okay. And the comment I mentioned a while back was that anytime you end up with a lone pair in the central atom, without any going any further, you know you have a polar species, okay? A polar species. And so you can go through this exercise for PCl3. You can see we got 3 polar bonds, okay? And they don't cancel out. You would think they would cancel out like the tetrahedral, but because of the lone pair pushing that bond angle shorter, they don't cancel out, resulting in an overall polar molecule. Okay. We did talk about carbon dioxide, and that carbon dioxide ends up to be a nonpolar species. And you can witness this because, you know, when you take your soda pop and you shake it up, what happens to it? Carbon dioxide spills out, right? That's because carbon dioxide is not really truly soluble in water. It's dissolved in there, but not soluble. And so when you shake it, you force it out and it gushes out. That's because carbon dioxide is nonpolar, even though they have polar bonds. Because the polar bonds cancel each other out, it ends up with a nonpolar character overall for the molecule. All right, so you might work on these. Okay, we've done water already, but practice on that on ammonia, and then determine whether this is polar or nonpolar. And if you have any questions, you might want to bring it on Thursday. We can go over this, because what this whole chapter is about is this. We talked about writing Lewis dot structures, and for the atoms, and then for the elements, and then from the Lewis dot structures, once we know that, we identify who's got polar bonds. Okay, make sure that they don't cancel each other out, and if they do, we end up with a nonpolar molecule. If they do not, let me restate that. If the molecules are all nonpolar, then we have a polar molecule. If the molecule has polar bonds and they do not cancel out each other, okay, you have a polar molecule. If they cancel out, then we have a nonpolar molecule. And that polarity then tells us, when we start talking about, when we get to that stage, what kind of force is involved with respect to the molecules interacting with each other. And that's going to tell us things like who's going to boil at a higher temperature, and who's going to have a higher surface tension, and so forth. We'll get to that, but it's all related to this. So you got to make sure you grasp this part of the chapter. Okay. All right. Well, let's stop it there. We will continue with chapter 8, which is a very short chapter. And